Good morning. Welcome to Breaking Encrypted Databases, Generic Attacks and Range Queries in Lagoon GHI with Marie-Seurat Lacharite. Before we begin, a few brief notes. Stop by the Business Hall located in Mandalay Bay, Oceanside, and Shoreline Ballrooms on Level 2. The Black Hat Arsenal is in the Business Hall on Level 2. Lunch is in Bayside AB from 1 to 2:30. Don't forget the merchandise stores on Level 2 and session recordings from SOK. They have a desk on every level. Thank you for putting your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick it up. Please use the microphone in the aisles for any questions following the talk. And with that, let us welcome our speaker.
Thank you. So first, a little bit about me. My background is in mathematics, and I'm a researcher in cryptography. I studied math at the University of Waterloo in Canada, then went on to do a PhD at Royal Holloway in the UK. I'm now working as a security consultant with NCC Group Cryptography Services in New York. My PhD thesis is about building and breaking encrypted search schemes for numeric data, and that's what I'm going to talk to you about today. 2 attacks that my colleagues and I developed and analyzed during my PhD studies. The motivation for my research is data breaches. Thousands, if not millions, of organizations store our sensitive information, whether that's medical, financial, or personal. Here's a selection of data breaches and the number of records compromised from just this year. Data breaches have become so common that there are now services like Have I Been Pwned that will check if your email or user ID appeared in the latest leak. I like thinking about whether we could use cryptography to make these leaks less harmful while keeping whatever functionality is needed on the stored data, the reasons it was stored in the first place. For example, is there a way to encrypt medical records so that policymakers can still efficiently query the data to look for trends and make decisions, but someone who runs off with the disk on which it's stored gets nothing but useless encrypted data? Or maybe a curious data center employee doesn't get access to the data, even though they're sysadmin on the database server. I'm interested in both creating and attacking these special cryptographic techniques, but of course, since this is Black Hat, I'll focus on the attacks today. I'll tell you how leakage from encrypted databases can be exploited by an adversary. I'm going to introduce these encrypted database attacks by telling you about them through a lens you might be more familiar with, side channel attacks. These are attacks that exploit vulnerabilities in the implementations of algorithms or protocols, not the designs of the algorithms or protocols themselves. For example, if 2 parties are communicating, a side channel could be the voice of the voice in which they're talking, the identities of the 2 parties, how long the message is, or the volume of the conversation, or when it happens. And of course, if these 2 parties are machines, there are many other side channels like power consumption, electromagnetic radiation, memory usage, CPU usage, cache usage, and so on. What's leaked through these side channels can reveal information about the actual message contents, or if cryptography is involved, something about the secret key. So for example, there have been side channel attacks on keystroke recovery from timing information in interactive SSH mode. There's been video stream identification based solely on traffic burst analysis of an encrypted video stream. And a classic cryptographic side channel, you can use error messages about whether or not a ciphertext decrypts to have correct padding or not, to actually decrypt that ciphertext. What we think about as side channel attacks actually have a lot in common with attacks on encrypted databases. They're all about exploiting leakage or unintentional information leaked from communication between 2 parties. In encrypted database attacks, the 2 parties are a client who queries its data to retrieve particular records or rows based on their values, and a database server who's hosting the data. This briefing is about new kinds of side channel attacks that can break database encryption. They exploit leakage from numeric range queries, like which records have values between 1 and 5, between the client and database server. These attacks exploit what we call access pattern leakage, or which rows in the database match the query, and volume leakage, which is how many rows match the query. The attacks use this leakage to break encryption. Even if everything in the database is encrypted, an adversary can figure out the plain text if these side channels exist. So I'll start with an overview of existing approaches to securing outsourced databases that allow range queries. These will cover different scenarios, like trusting the database server but not the network, or trusting the database server but being worried about the risk of disk theft, or not trusting the database server. Then we'll get to the attacks. I'll explain how exploiting this leakage can lead to breaking encryption in the databases. Finally, I'll share what I think are important points for practitioners to consider when evaluating such schemes for their organizations. Here, again, is our basic architecture. We have a client on the left and a database server on the right. The server is storing a database, which you can picture as just a table with two columns. The first column is the primary key, which is unique for all rows. Here, we just assume it's sequential for simplicity. The second column is the value, a number between 1 and n, which is the attribute that the client is going to select rows on. For example, in a medical database, ID could be some kind of anonymized patient identifier, and value could be the patient's age, for instance. The table could have more columns, but for this setting, we assume the client always queries records based on just this one. And the type of queries the client makes is range queries. It always retrieves records based on whether their value falls in some continuous numeric range, like 1 through 5. If you're familiar with SQL, this would be a query of the form select star from table where value between x and y, the two endpoints of the range. But the particular query language or database engine isn't important as long as two things hold. First, the client always makes range queries over some finite set of values, which we can assume is the integers from 1 to n. And second, that the database server always correctly returns the IDs of rows whose values fall in that range. Securing data is all about understanding the threat model. Historically, protecting queries and results from a network eavesdropper was the first step. The client and server can protect their communications by encrypting them. We know how to do this. We have TLS. The client and server can use that for authentication and negotiating a session key to encrypt the queries and responses, so anyone who sees the packets doesn't know what the query was or which records in the database matched it. But of course, encrypting data on the wire doesn't protect against everything. As people began to outsource their data to the cloud or big data centers, they had to update their threat models to account for the risk of disk theft, which, as we saw before, actually still happens in real world. Encryption at the file system level or column level addresses this issue. Suppose the client wants to query its data. Usually the process goes like this. It uses TLS to encrypt its query and sends it to the server. The server decrypts it, consults its search index, and fetches the relevant encrypted pages from disk. It decrypts them in memory, processes the results, re-encrypts them, and sends them back to the client. Whatever's on disk stays encrypted the entire time, so even if someone breaks in and grabs the hard drive, they won't see unencrypted data. Pretty much all major database vendors offer some variant of this, usually called transparent data encryption or native encryption. These solutions usually don't have any noticeable effect on performance. The server can still index the plaintext data, so range queries can be answered efficiently. Some of these solutions also offer more granular field-level encryption, like format-preserving encryption or tokenization. But the data encryption key is usually still managed by the server in a key store attached to the server, hopefully not on the same disk as the data itself. But even if the data encryption key isn't stored on the same disk as the data, it's often accessible to curious database administrators, sysadmins, or anyone who gains such permissions. To prevent a full database server system compromise from revealing this stored data, it needs to be encrypted by the client itself or via proxy before it even gets to the server. But if the data stays encrypted the whole time, how can it possibly be queried? To me, this is the problem with the most interesting solutions, not only because they ensure the database doesn't see raw, unencrypted data, but because there are some really cool techniques that allow efficiently retrieving that data. In industry, these solutions are usually called client-side field-level encryption. Instead of being in a key store attached to the database server, the data encryption keys are entirely controlled by the client. Such solutions are offered, for instance, by Microsoft in their Always Encrypted products, which offers field-level encryption in client-side drivers, or MongoDB's upcoming 4.2 release. Also, companies like CipherCloud offer encryption proxies. Usually, these client-side encryption solutions offer only two types of encryption, deterministic and randomized. Let's take a closer look at these two types, and then a third type called order-preserving encryption. As we'll see, one of these leaks repetition in the plain texts and makes range queries possible but inefficient. One of them is secure but doesn't support range queries at all. And one leaks order but makes range queries as efficient as on plain text. So deterministic encryption is probably the most widely used way to support queries on encrypted data since it leaks equality. But it doesn't offer much more functionality than that, only exact matches. With deterministic encryption, any repeated plaintext values show up as repeated ciphertext values. In this example, each row that had a value of 0 will have the exact same ciphertext. This makes range queries possible. Instead of requesting all records with values between 0 and 3, the client can request all records whose values are in the set of encryptions of 0 or 1 or 2 or 3. Although range queries are possible, the fact remains that any repetitions in the plaintext will show up in the ciphertext, and this can be exploited when combined with just a little information about what the distribution of values actually is. These attacks were evaluated on medical data sets by Naveed, Kamara, and Wright, and many others after. With randomized encryption, the server can't index the data or group values. Using randomized encryption would make all encryptions of 0 different, but then the server would have no way to select all of the records with value 0. Order-preserving encryption is another method of encrypting numeric data, which does exactly what it sounds like. If the plaintext A is less than the plaintext B, then the ciphertext for A will be less than the ciphertext for B. This allows range queries and sorting over the ciphertexts. If the client encrypts values with OPE before sending them to the server can still index the data just as if it was clear text, unencrypted, but it doesn't learn the exact values. When the client wants to perform a range query, all it has to do is encrypt the endpoints of that range. So for example, a query for records with values between 0 and 15 would become a range query for ciphertext between, say, 84 and 2307. Unfortunately, it was proven that even an ideal order-preserving encryption scheme, the one that behaves like any old random order-preserving function, has to leak a lot more than just the order of two plaintexts. In particular, about half of the plaintext bits leak, and therefore, this doesn't offer much security, especially when the scheme is deterministic and additionally leaks which values are repeated. This motivated new schemes that sacrificed a little bit less security while still allowing range queries and sorting. These include techniques like order-revealing encryption, which is just a generalization of order-preserving encryption. Instead of directly looking at the ciphertext to compare them, you need to compute a function over each pair of ciphertexts to know which one is smaller. And there are other schemes that do more complicated things, like build a search index that the server can traverse itself, destroying nodes along the way as it goes. These schemes leak a lot less than OPE, but they still leak something. Now, suppose you combine all of these types of encryption. You encrypt the queries and responses between the client and server, you encrypt data at the page level, and you have the client encrypt everything before even sending it to the server. What could still leak to the adversary via side channels? Well, the server needs to know which records match the query in order to return the correct results. So the identifiers of the records that match the query, in other words, the access pattern, can leak. Second, even though the client-server traffic is encrypted, there's no hiding its length. So the number of records that matched each query can also leak. We call this volume leakage. The key point is that regardless of which fancy encryption or combination of types of encryption is used, practically all schemes leak which records matched a query or how many records matched it. How exactly this leaks can vary. It could be from someone man-in-the-middling the responses from the database to the client. It could be getting access to logs for undos and redos or query profiling. on the server, or it could be from an adversary just observing traffic volume. For an in-depth look at where such leakage can arise in the case of a MySQL server, I recommend my colleague's paper, Why Your Encrypted Database is Not Secure. It's an important question to extract this leakage and exactly how to do it, but it's orthogonal to what I'll present today. I'm going to focus on what we can learn once we have this leakage. In this first part, we saw various ways to secure a database. Encrypting the connections between the client and server protects against eavesdroppers. Server-side file system level encryption mitigates disk theft. And client-side encryption of data can make data entirely inaccessible, even to the database admin. But even when all of these protections are used, some information still leaks. Now we come to attacks on leakage from range queries on an encrypted database. As you recall, here's the model. The client makes a range query whose endpoints are hidden, sends it to the server. The server finds the matching rows and then sends back the matching row IDs to the client. Somehow, some way, the adversary learns what those row IDs are. It learns which records match the query. So what can it deduce about values in the database? Range queries have some pretty important properties. Let's look at an example. Consider this database with 10 records. Suppose the first range query matches records 2, 3, 5, and 10. And then there's a second range query, and the adversary learns it matched rows 1, 2, 4, 5, and 8. The adversary has actually already learned something. Range queries are continuous intervals. Since records 2 and 5 were matched by both queries, their values must be between the values of records 3 and 10 on one side and 1, 4, and 8 on the other side. Let's take a closer look. The adversary knows there are 10 records. After observing 2 queries, it can split the records into 4 sets based on whether they matched either query 1 or 2 or both or neither. Since each query has a corresponding range of values and the intersection of 2 ranges is also a continuous range, we can actually order 3 of the sets of records like this. The adversary can deduce that records 3 and 10 have values less than records 2 and 5, which have values less than records 1, 4, and 8. It hasn't learned anything about records 6, 7, and 9 yet. One way to use this is, for example, suppose the adversary happens to learn through some other side channel the value of record 2. Then it learns some bits of information about the values of records 1, 3, 4, 8, and 10. As the adversary observes more queries, they can keep performing these set intersections to group together the records and sort them by value. But there's an easier way. There's already a data structure we can use to encode the information in access pattern leakage. It's called a PQ tree, and it was discovered nearly 45 years ago. The idea of using a PQ tree to order records in a database isn't new, but it was never used to actually reconstruct the values like we're doing. A PQ tree has 2 types of nodes, P nodes and Q nodes. Its purpose is to encode a set of orderings on some base set, here 1, 2, and 3. The children of P nodes can be reordered in any way. For example, if a P node has 3 children, then there are 3 factorial or 6 possible orderings of its children. The children of a Q node, on the other hand, can only be reflected. There are only 2 possible orderings of its children. We're going to use PQ trees to keep track of what are the possible orderings of the records based on the access pattern leakage. Once we have them in as many groups as there are possible values, we'll have worked out the exact value of every row in the database. Going back to the example with 10 records, we'd start with a single P node with 10 children. All orderings are possible since we haven't observed any access pattern leakage. After seeing the first query, we essentially need to rearrange the items in the PQ tree so that the records that matched it are next to each other. So the tree gets a new child P node with the 4 records that matched as its children. After the second query, we again need to rearrange the leaves so that the ones matching the query are next to each other. Now things get more interesting. A Q node appears. It has 3 children, one for each group of records that matched only the first query, one for the group of records that matched both the first and second query, and one for those that matched only the second query. The 3 records that haven't matched any queries are children of the root P node. As we see more queries, we can keep reducing the number of orderings in the PQ tree using the access pattern leakage. The procedure to do this is a bit tedious with lots of cases, so I won't present the details. What's happening, again, is that we need to rearrange the nodes of the PQ tree so that whatever leaves matched are continuous. And all of the orderings encoded in this tree, they're next to each other. After a while, with enough different queries, we end up with a PQ tree that has a Q node at the root. What this means is that we figured out the order of all the records, from smallest to largest, or largest to smallest. The Q node's children are groups of records with the same value. If 2 records have the same value, then they have to match exactly the same set of queries. There can't be a range query that matches one of these records, but not the other. And now we actually have enough information to determine the value of every record. The first group is records with value 1, the second group is records with value 2, and so on. The adversary can completely reconstruct all values in the database. Now, you might be wondering, how many queries does the adversary need to see to get the leakage of to get this far? Clearly, if it sees leakage from only one query repeated over and over and over again, the attack isn't going to succeed. To analyze how many queries are necessary, we need to assume that the queries the adversary sees are sampled from some fixed distribution, say the uniform distribution. Every range is just as likely as every other range. Then we can apply some powerful results from statistical learning theory to say that with high probability, after some number of queries, the attack will succeed. Specifically, if the values in each rows can have one of n possible values, in other words, if our goal is to get a PQ tree consisting of one Q node with n children, then the number of required queries is about n log n. So if there are 100 possible values, then after about 500 queries, the attack will succeed. So for instance, if we're doing this attack on a database of patient ages, it would take about this many if queries are chosen uniformly at random to determine every patient's age. Now, if you were paying close attention, you might have noticed that this approach relies on there being at least one record with every value from 1 to n. But we can actually adapt the analysis to count how many queries are required if all we want to do is get sorted groups of records whose values are close enough. This applies when there isn't at least one record with each of the values from 1 to n. For this kind of approximate reconstruction, the number of required queries no longer depends on n. It depends only on how close you want the values to be relative to n, which to me seems a bit magical. For example, to group together records whose values are at most 5% apart, you need only 60 or so queries, regardless of whether that 5% is of n equals 50, or n equals 500, or n equals 5,000. This attack showed how access pattern leakage is sufficient to order all records and group them by value, from which we can deduce the value of every single row in the database bypassing the encryption. It uses a PQ tree to encode the leakage along the way. Even without the leakage from sufficiently many queries to exactly determine the values, it's possible to approximately recover the values. And if you want more details, have a look at my paper. Access pattern is pretty significant leakage, and in your threat model, maybe it doesn't leak to the adversary. Volume leakage, on the other hand, can be observed more easily. You don't need to be a persistent adversary who's compromised a database server to know how many records matched a query. Even a network adversary could have access to this side channel just by monitoring network traffic. But of course, the number of records matching each query could leak in some other way, in server-side log files, for instance. There are plenty of settings where an adversary can't see access pattern leakage, but it can see volume leakage. Suppose that somehow, some way, the adversary learns how many records match every possible range query. It has the entire set of possible query volumes. It doesn't know which query corresponds to which volume, it just sees the volumes. It's going to use these volumes to determine exactly how many records there are with each value in the database. If the query distribution can be modeled, it's possible to figure out, again, how many queries a network adversary would need to observe before it gets all volumes. I'll say more about that later. So whether it's by observing queries or finding some valuable log file on the server, the adversary learns the set of all possible query volumes. Let R be the maximum observed volume. This has to be the volume of the entire range 1 through n, also the number of rows in the database. The idea of our attack is to identify what we call elementary volumes among the set of all volumes. Elementary volumes are the volumes of elementary ranges, which are the ranges from 1 to 1, 1 to 2, 1 to 3, and so on, up to 1 to n. If we can identify which volumes correspond to the elementary queries, then we can deduce exactly how many records have each value. Just subtract the volume of the kth elementary query from the k plus first elementary query, and you get the number of records with value k plus 1. The attack succeeds if we identify the set of elementary volumes, so this is now our goal. Elementary volumes and ranges have some pretty special properties. First, every elementary range has a complementary query such that the sum of their volumes is exactly R, the total number of rows in the database. This is because any elementary range 1 through I, there exists the query 1 plus I through n, and their volumes have to add up to R. So every elementary range is R complemented, we can say. Second, any possible range with any two endpoints either is an elementary range or is a difference of elementary ranges. If the left endpoint is 1, it's an elementary range by definition. If not, we can write it as the difference of two elementary ranges, like you see on the screen. And the third property is that the difference of any two elementary ranges is also a range. So the difference of any two elementary volumes also has to be an observed volume. We're going to build a graph to identify these elementary volumes using the three properties along the way. First, the nodes of the graph are all of the observed volumes. Next, we'll draw an edge between any two nodes if the difference of their volumes was also an observed volume. In this example, there's no edge between 12 and 8 because their difference 4 was not an observed volume. The crucial observation is that in this graph, there will be a subgraph of the elementary volumes. Their nodes in this graph will form a clique, which is a subset of nodes that are all directly connected to one another. This is a maximally connected subset of nodes. And this is because of property 3. The difference of any two elementary ranges is also a range, so there must be edges between every pair of elementary volumes. Further, the volumes generated by that clique, the volumes of the nodes themselves, and the differences of volumes, which we can assign to the edges, have to generate the entire set of all volumes. This is because of the second property. Every range either is an elementary range or is a difference of two elementary ranges. So using these properties of range queries, we build a graph using the observed volumes. The properties mean that if we find a clique and it generates all volumes, we've identified the elementary volumes from which we can reconstruct all element counts in the database. So all we have to do is find a clique in this graph and we're done. But in general, if you remember some graph theory, this is a pretty hard problem. However, we can use some tricks to find a clique efficiently in most cases. Our reconstruction algorithm has two phases, pre-processing and more traditional clique finding, which isn't always needed, so I won't talk about it much. Specifically, in the first phase, pre-processing, what we'll do is grow a set of necessary elementary volumes and shrink a set of candidate elementary volumes until they're the same set, in which case we've identified the set of elementary volumes. We'll do this by alternating reducing the set of candidate volumes and augmenting the set of necessary volumes. So let's do an example. Here's our starting graph. Each volume gets a node, and there's an edge between two nodes if the difference of their volumes was also an observed volume. To start, all the nodes are candidate elementary volumes in green. Now first, we'll reduce the set of candidates using property 1. Any node that doesn't have an R complementary volume is out of the candidate set. So for example, volume 5 has no complement because there was no range query with volume 15. So 5 is out of the set of candidate elementary volumes. Next, we can build up the set of necessary elementary volumes by adding the smallest and largest complementary volumes. The largest must be the total number of records, R, the volume of the range 1 through n, an elementary range by definition. And because of properties of elementary ranges, the smallest complemented volume must also be an elementary volume. Then we go back to pruning the candidate set. We can remove all nodes that aren't adjacent to all necessary elementary volumes in orange, since we're looking for a click, and every node is adjacent to every other node in a click. So maybe you can see the click now, but we'll do one more step. We go back to augmenting the set of necessary volumes. 5 was an observed volume, and it arises in only one way in the current graph, as the difference between the volumes 12 and 17, an edge between two candidate volumes that aren't yet necessary. Since every volume is either an elementary volume or the difference of two elementary volumes, and we observed volume 5, this means 12 and 17 must be elementary volumes. And now we're done. All nodes are necessary, and we can see that these 4 nodes generate the entire set of observed volumes. So to exploit volume leakage, we first built a graph using all of the observed volumes. We used properties of range queries to identify the special elementary volumes, which form a click. Then we used the elementary volumes to directly reconstruct all counts in the database. With only volume leakage, it's impossible to know whether we've recovered element counts from smallest to largest or largest to smallest. If the element counts were mirrored, we'd still see the exact same set of volumes. So what we've constructed is actually the counts of all elements in the database up to reflection. One last thing I said I'd come back to. How many range queries do we need to observe to get the complete set of all range volumes? To analyze this, we need to model the query distribution somehow. So suppose all ranges are equally likely. Then we can apply what's called a coupon collector bound. In general, this tells you if you have a bunch of things and you pick one at a time blindly at random, then put it back, it tells you how many times you'll need to repeat this until you've chosen each of those things at least once. Here it applies with the things being all the possible range queries. So using this coupon collector bound, we can say that if queries are drawn uniformly at random, the number of queries until the adversary has seen all volumes is about n squared log n. If you're interested in more details about volume attacks and some extensions to them, like if a record's value is updated, how to recover that value, or if a record is inserted, how to recover its value, have a look at my paper. Leaking access pattern and volume of query results can be devastating and lead to bypassing database encryption, regardless of what type of encryption is used. So what can be done? I'm not a risk management expert. I can't tell you which threat model is right for you, but I can suggest what to keep in mind when evaluating a solution. So here are some recommendations for practitioners from my point of view, the point of view of a cryptographer. I suggest analyzing leakage from 2 angles. First, making a comprehensive list of all types of leakage that could occur in your solution. And second, looking at specific points or operations and thinking about what type of leakage could arise there. Leakage can arise from properties related to values, queries, and responses. Besides leaking the actual values themselves, the records can leak the ordering of values, existence of certain specific values, the number of distinct values, the distance between values, whether values are repeated, and so on. The repetition allows frequency analysis attacks. An adversary that already knows a little bit about the distribution of values can infer a lot about specific values if their frequencies are leaked. Queries can leak information about the endpoints, when a query is repeated, the width of the range, when one range is a subset of another range, and so on. Besides leaking which rows matched or how many rows matched, answers to queries can also leak, for example, when two sets of matching records are the same, or which records match the most queries, or so on. For a pretty comprehensive list of the types of leakage, I refer you to Kamar et al.'s paper, Structured Encryption and Leakage Suppression. Next, I suggest you think about what points in the implementation all these kinds of leakage could arise. For example, it could be when you do an initial upload of rows in the database. It could be during this bulk upload or a single insert later on. It could be when you make a single query or when you make a batch of queries or when you're profiling the queries. It could also be when performing some maintenance operations like backups, key rotation, or updating the search index. You can do a kind of differential analysis. What changes in the adversary's view when two things are not the same? There's no magic solution when it comes to side channel leakage. You're going to have to make some trade-offs in your encrypted database solutions. So in addition to considering what could leak and where, you can think about which of the following techniques for mitigating leakage would be acceptable. You could restrict the type or granularity of queries. For example, for range queries, you could force the endpoints of the range to always be multiples of 5 or 10. You could add dummy records to your database. If you're using a solution that leaks frequency information, this could help hide frequency information, making all values appear equally likely. You could also make dummy queries. If you leak some information about the distribution of queries, you can smooth this out by adding dummy queries. And of course, you can also trust hardware on the server. Now, what you'll be trading for more security could be things like incomplete query results, so you get almost all records in the range you requested, or it could be just probabilistically correct results with either false positives or false negatives. And a common trade-off is sacrificing efficiency when querying the data. So maybe a range query takes multiple rounds of interaction with the server, or maybe there's some post-processing of results necessary on the client side. Or maybe this means that on the server, you can't do any compression of values or deduplication of data, or you can't batch queries. Different trade-offs can be acceptable in different situations. All right, we made it to the end. This briefing was about new kinds of side channel attacks that can break database encryption for numeric data. The two kinds of leakage we considered, access pattern leakage and volume leakage, can arise from, say, an adversary who's compromised the database server or just a network eavesdropper. An adversary can use access pattern leakage along with a PQ tree to figure out the value of every record in the database, either exactly or approximately, bypassing any encryption. Using volume leakage, an adversary can create and prune a graph to identify these special elementary volumes, which in turn will lead to completely determining how many records have each value. These attacks apply to any kind of scheme supporting numeric range queries that have these side channels. There's no simple way to eliminate this leakage in all threat models, nor are access pattern leakage and volume leakage the only kinds of harmful leakage. But there do exist some countermeasures, like adding dummy records, making dummy queries, or increasing the amount of client-side post-processing of query results. At the beginning, I suggested thinking of encrypted database attacks as side channel attacks, and we can learn something from there. The Bleikenbacher padding oracle attack, which was from 1998, is still regularly found in the wild today. If we don't take side channel attacks on encrypted databases seriously now, I think they could be with us for decades. So it's worth it to analyze what we can learn from side channel leakage. Thank you. I'm happy to take any questions.
Hello. Thank you very much. That was really interesting and fascinating. And if your answer is going to be, I should read your paper, that's fine. But I didn't get how, in your example, you could see that node 5 did not have an R complement.
Okay, so we had the entire set of query volumes. We assume that our set of observed query volumes is complete for every possible range query. And we had that the maximum of those volumes was 20, I think if I remember correctly, the total number of records. So 20 is the value of the range 1 through n. And there was a query with volume 5, we don't know which range, but there was no query with volume 15. So there was no R complement, as we say in that way. Does that answer your question about how we could see whether?
Thank you very much.
Yes, thank you for your question.
Yeah, I'm in the center.
Thank you.
Small guy right here.
Blinded by the lights.
How did you find the PQ tree data structure?
Research.
Yeah, and I mean, I'm always curious how people go about doing this, and what type of research did you do to get it?
One of my colleagues found it in this instance. I don't know if he uses some special academic search engine or just spent hours and hours looking at old theoretical computer science papers. I'm not sure. That's a good question. Probably lots of Googling of different query terms. Thanks.
I'm over, yeah, you're looking at me now. Doctor, thanks very much. This is a really interesting talk. I'm blown away. I'm mostly interested in the protective aspect, and you totally lost me near the end when you talked about using dummy queries as a mitigation strategy. Is the idea just that we're going to flood extra legitimate queries from the client so that the observer has to observe more transactions before they can build their model? Or are you talking about somehow returning illogical, like disjoint ranges to stymie the building of their model?
That's a very good question. How can making dummy queries help with these kinds of leakage? So for access pattern leakage and volume leakage, I don't think they actually help mitigate any vulnerabilities there. But there are other attacks that work using the distribution of ranges. So it assumes that the queried ranges have some distribution, and using, say, the distribution of volumes, how many times you saw on average a query with a certain volume, you can use that to attack volume leakage. So for the attacks I presented, it's not a countermeasure because we don't care about the distribution of queries, but there are other attacks. I can point you to one paper by Kolaris et al., where they use the distribution of queries to attack volumes. Great question.
Thank you very much.
Thank you.
One more question
Hello.
here. Great presentation, by the way.
Thank you.
One question I had is when you're doing these modelings of analyzing all these numbers and so forth, did you take into consideration eventual consistency versus strong consistency in the databases and how that might have an impact on those volume numbers that you're trying to extract?
No, I didn't. I'm actually not familiar with those types of consistency and how they would affect our attack, but that sounds like an interesting real problem to consider.
Thanks.
Thank you for your question. Thank you.